several algorithms about recommender system personalization. The first we'll talk about is a general, general idea of personalization, and then we're going to focus on this very simple, straightforward technique called similarity-based approach, and then we're going to provide a justification. The similarity-based is really heuristic. Okay, think that should work, but is it mathematically sound? So we're going to talk about a probabilistic justification. A very bit, just a little bit about a math behind it. I think after this, you'll definitely be able to implement user-based or item-based. I think some of you guys already decided the group project, even the thesis project, looking at personalization and recommender system. So today might be quite important for you to, so that you would, if even you might know some of the algorithms. So today you might have a thorough study about personalization and recommender system. And then we're going to focus on a popular technique called singular value decomposition, SVD approach, which is proved to be very effective in quite a number of competition going on for the last few years, especially Netflix competition. And in the Netflix competition, in that context, we're gonna talk about the temporal dynamics, because people find that there's a temporal dynamics or some behaviors, user behaviors, and also item rating change over time. And if you're able to find technique to deal with that, in fact, it's helped a lot in terms of improve the accuracy of your prediction. After that, we'll have some discussion about other issues in personalization recommender system. So just give that we only have 3 hours talking about personalization. We're going to look at these 2 examples. Say, okay, we're going to look at cold start problem. What if the user does not provide any rating? Can we still make the suggestion or recommendation personalized? We're going to talk about cold start problem. And then we're going to talk about security, privacy, not privacy, the security issue. That what if someone provides a fake profile trying to promote some product? Can we prevent that from happening? Which is called shilling attack. We're going to prevent shilling attack. Talk about several techniques. In fact, the technique we're going to talk about was developed by one of our master students. He did a very good job on the thesis. So it might give you a bit of hint as to what sort of thesis you would be able to produce as a master student. Okay, so let's have a brief discussion about. This is a concrete example from Amazon. I believe you guys, definitely have experience of buying books in Amazon or other online on our website. So this is what Amazon provided. If you look at this book, it basically provides that people brought this item, also brought that item. That's very simple statistics, but work quite well when you have no clue as to what specific book you want to buy, but you have a general idea in terms of a certain topic. You want to know something, you want to read a novel by Dan Brown, and you start with search and get the item and explore the possibilities, and look at the ratings and so on. The simple statistics here is quite efficient in terms of for you to find what you really want. And so the question is, how can you get user profiles in order to provide a personalized recommendation, or in order to calculate statistics about user behavior? One thing you can get is by asking user to rate items that they like or rate items that they hate, right? Or other is that we're not going to ask the user to provide, but instead we're gonna learn from user behavior. So Amazon in fact have this your interface which you can in fact provide rating of the item that you purchased in the past. And this is another example that you can also not only the books, you can also rate movies, for example. And iTunes, Apple took a different approach. Here example in iTunes where when you play the music, you can automatically sort of learn your listening habit. For example, if you keep listening certain artist music track quite often, then you might have a strong indication you actually like that artist. So you might have a strong indication that you might like that type of music. So here is the illustration. If you have the profile, and how can you, so what is recommendation problem and how can you actually address it? Let's say you got this matrix. Once you collect the user profile, and here's a small illustration. You got, let's say, a set of users, and then you have a set of items. So in this case, it's movies, and the element here is basically this guy, the 5 star for that particular movie, Golden Line. And then once you have this user item matrix, what you can do is that obviously you can build a profile for this guy in terms of what are the things he likes and what are things he doesn't like. And equally, you can also build a profile for a given item as well, not by the content feature. We have talked about text retrieval, which is we talk about content description and use it to describe the document. Here, instead, we can look at the user ratings, consider them as a feature to represent that particular item as well. So that gives you additional channel to understand the item. Sometimes it's quite useful and much better than the content description, because that is user behavior. That is something to do with the user taste, where you have this textual document, text data. The text data might not necessarily tell you about users' interest. So in the Netflix competition, and then people in fact try to get content description, try to make prediction, but they're never able to beat the collaborative filtering approach, which purely taken this user profile data to try to make prediction. So anyway, so what is recommendation program? So here is that because you have this metric, potentially this metric will be very, very big, very low. Think about this. You might have millions or more than millions items. You might have more than millions users. Then this metric is going to be huge. And in most cases, because you don't have observation, user not able to read all the movies, right? Therefore, this matrix is going to be very sparse. And there are a lot of missing data. And for example here, what collaborative filtering task is, or what personalization task is, in fact, is that to understand and try to make a prediction about those missing values. Basically try to ask is, if the borrowers watched Love Actually, whether he gonna like that movie or not, what would be the rating this guy gonna provide? So that's in fact is a personalization question, or is a recommendation question. Because once you have that prediction, obviously you can make a recommendation. So the user-based collaborative filtering is that we can in fact identify, because we have a profile to represent each individual user, right? Therefore, we would be able to identify like-minded users, like-minded people, given your profile. We can find other people who have the same taste as you. So one thing you can look at is that if you rate items similarly in the past, you have a similar rating in the past, then it's likely you are like-minded people. So the recommendation, as I said, recommendation question is that if Boris watched Love Actually, what would Boris rate it? So this is collaborative filtering program. Can you have a guess what the prediction would look like? Whether Boris is gonna watch film Love Actually or not?
Not.
Not.
Good start.
Why?
Based on George upload.
Sorry?
With George profile.
Uh-huh.
So I think they're quite similar.
Why is that similar?
Because the first three movies they gave almost similar stars.
Okay.
Then after that, George actually gave 2 stars for Love. So
Okay.
I think we can infer something from that.
Okay, that's correct. Can you look at it from the user perspective? So you look at this rating, right? Because George is quite similar to Robert, therefore you can use this to infer that. Right? Can you look at the other way around? Another direction, let's see. From the can be using those ratings to infer that.
It's difficult because it's different genre.
It's different genre. I mean, look, whether can you use
Yeah, so the user seems to like action movies.
Yeah.
And the one with the 1 star seems like it's not an action movie.
Yeah.
So most likely you wouldn't be into a romantic kind of movie.
Yeah. But think about this this Amazon case. People brought this, also brought that. So do we have that similar? We could be using similar insight, similar.
Will rated both.
Sorry.
Will rated Titanic. No. Will rated Notting Hill and looking at the columns.
Yeah.
Notting Hill and Love Actually share the rating for Will. So you can kind of compare that. From looking at this column and this one, that's gonna.
Okay. So what if? So instead of calculating similarity between users, you can also calculate similarity between items, right? If you calculate similarity between items, there perhaps Notting Hill is quite similar to Love Actually. Therefore, you can make some. Right. Okay. So I mean the point here is that what you can do is look at one way is that to look at the similarity users. So in this case, you can calculate similarity between users. In this case, Boris is quite similar to Dave and George in terms of the ratings they got. For example, they both like action movie, and they both not really like romantic movies. Therefore, you can somehow make prediction from this rating, put them together. So this is a very simple idea, and it turns out work quite well. The simple algorithm works as follows: it's first find similar user, that's it, and then based on the similar users and recommend items. Look at the behavior of the other similar users, and to see what are the items they are interested in, and make a recommendation based on that. And the first question, obviously, is how can we come up with a sensible similarity measure? If you plot these user ratings against items, right? So let's say each curve here in this graph is a single user. Therefore, you will have a different pattern, right? In terms of the ratings that you would have across users. If you say compare two users, you can compare, let's say, the user yellow and the user blue, and look at their ratings. You can find that, in fact, they are somehow correlated. Or in other words, these ratings are all always in the diagonal. Whereas if I rate higher for a certain movie, and another person would rate higher for that certain movie, if the yellow user rate low, and the blue user going to rate low. So that means it's perfectly correlated, isn't it? Therefore, you would have a very reasonable guess if the blue user likes certain movie and the yellow user going to like, right? Or the other way around. Whereas if you look at user black and user blue, then the pattern is different. Therefore, perhaps you wouldn't be able to make prediction by looking at one of these users. However, if you look at another pair, let's say user purple and user blue, although these have this similar pattern as the previous one, but they had a bit of drift in terms of user purple. For example, when the user have rating 5, user purple has a rating 5, user blue might have rating smaller rating. But the trend is there. If you rate higher, I will rate higher. If you rate lower, I will rate lower. So that means this still help us to make a prediction, but we probably need to take into account the user has a different offset. So why user have a different offset?
We have different rating threshold. I like to rate higher than average.
So some user might have a general preference. So this guy may like everything. They might appreciate everything. Therefore, all the ratings this guy give is very high scores. Whereas you might have some people very conservative, and therefore the rating they give, even though he might very like the movie, but they never say 5, but they might say 4 or 3. So that suggests that we need to, number one, we need to consider correlation, but number two is we need to because there's offset between different users, different offset between different users, therefore we need them taken into account. So the obvious solution would be Pearson correlation, where you calculate linear correlation, but take into account these the bias, the offset. You can take this using the means that you calculated. Another solution is that if you learn vector space model, you still remember vector space model. What we have used is cosine similarity. So here again, you can also using cosine similarity as a measure. So that if you look at the difference, there is that one is subtract mean, another one doesn't. So that's the difference. We will show later. If you're using this different similarity, the performance, in fact, is different. Sometimes one of them is slightly better than the other. Any questions so far? So far, so good, right? So this is once you have the similarity measure, and then you can come up with a calculation. So this is a very simple method. So the idea is that number one, you get these similar users, right? Once you get these similar users, and you look at their ratings, and then you average their ratings, and you get your prediction. So that when you do the averaging, you weighted average, because some are more similar, therefore you get higher weight. Some are less similar, therefore have a lower rate. So you can use different weight function for those ratings, and put them together, you get a prediction. So in summary, what you have is you get your neighborhood users, which is let's say UK here, UA here, and then you look at the ratings there, and normalized subtracts this guy's mean, and then weighted average across all the similar users. And the normalized, obviously, based on this, make sure that rating will stay 0 to 5. And then you correct by this average rating for that query user, for the given user. And you're done. So that's it. So this is very simple formula. Any questions about that? Make sure that you've been able to do everything, including that. So it's nothing new or nothing complete here. It's just you get top 10 similar users, and then looking at their ratings about that particular movie, and averaging those movies, and then and put them together, you get your prediction. That's it. So as I said, there's one way you can look at it, look at similar user, but equally you can look at similar items as well. So in this case, so instead of you looking for a prediction from the rating from other users, but you can also look at the ratings from this particular user to see whether these two items are similar, these two movies are similar. You can also propagate your ratings from a different direction. So you can be able to get that as well. I will show you an experiment later that sometimes user-based, sometimes item-based is better than the user-based. So again, the technique is quite similar. You first obviously need to find similar items based on a set of items, and then look at their ratings, and then be able to make prediction. And once you have for all the missing, the ratings that the user haven't really rate, you have a prediction. You rank based on your prediction and pick up the top end as your recommendation. That's it. So here, a slightly different is that when you calculate the similarity, you could using a Pearson correlation, but you can somehow change it. Instead of using the rating, average rating per user, you could say sometimes people test this, in fact, Pearson correlation, and subtract the mean rating for the user. It's not necessarily, in fact, it's not really improve the performance, but sometimes they actually not necessary to using item average. Therefore, cosine angle, in fact, sometimes work quite well. So this is a standard Pearson correlation where you subtract the ratings for this particular item, the average rating for this particular item. This is cosine similarity that we talked about when we talk about texture. These two are quite similar to user-based approach. However, people find that the cosine angles does not really take into account the different rating scale between users. So what you usually have is that you correct for average user rating. So this is called adjusted cosine similarity. So it turns out this adjusted cosine similarity actually perform quite well, and better than cosine similarity, and better than Pearson correlation. So note that the difference between the adjusted cosine similarity and Pearson correlation here is that here subtract the average rating per user, whereas in the standard Pearson correlation, you subtract the average rating per item. This is the only difference. And in reason why? So it seems that the offset from the users are much bigger than the offset from the items. Yeah.
Because you're predicting for users, so users would naturally be more.
Therefore, you need to consider that. You need to consider that per user. Yeah. So that is one of the reasons. In fact, it's because you just although it's a symmetric, but it's not 100% symmetric. It's you need to personalize user, not personalize item. And the other hand is that obviously when you have this data, you have user item matrix. Whereas if you look at each row user profile, obviously different user have different rating behavior. Whereas for the items, right, they don't for each individual item. They are not the one to have the rating. So they has been rated by user. So therefore, it's not symmetric in that sense. So again, if you do use an item base, you can follow the same thing. That you calculate the rating and you calculate similarity, and you do this weighted average across all the similar items you get. Note that here there's no need to do offset. You don't need to do offset because it's quite simple, right? This is rating. So this is the predicted ones. Whether I'm gonna like actually. So this is rating for also by rating, but for other similar movies. Therefore, the offset will be the same. You don't need to do the offset in this case.
So I was just wondering, neighborhood approaches, do they help using correlations by neighborhoods and then just picking using a neighborhood to make predictions?
Yeah. So these two, in fact, can be called a neighborhood approach. So it's exactly the same, but it's just different.
So I didn't actually
So this is more like checking how similar it is.
So I got distracted. Yeah.
And this is the rating for the neighbor. Then do that. So in machine learning, obviously there's another term called nearest neighborhood classification. So this can be considered as called nearest neighborhood regression, if you like, because indeed you're not going to predict a label, but rather you want get a value, get a real value. So it's a nearest neighbor regression. But I'm going to talk about this complex justification about why it's sensible using Pearson correlation. Why it's sensible that you have a weighted average. And any question? Any other question? Okay. So when we use this system, we know that we have the matrix and there's some of the missing data, and then therefore we fill in this missing data, make prediction. And how do we make predictions? So as I said, what you usually do is that you're gonna send a list of items to the user. So what you can do, you can rank predicted ratings, rank items based on the predicted ratings, and take the top and most or the highest scores, highest ratings, highly predicted, then rank and then say send this top 10 list. That's it. So the common data set is movie lens data set. I think some of you guys working on recommender system and a group project, so might already download the data set. The data set is usually relatively small, so about 1,000 users some item as well. So therefore, you'll be able to quickly, come in with your solution. So when I say the data is very sparse, so equally for this even small data, if you look at this, some statistics here, it's 93% of entries in fact is zero, it's missing. So what you can do is that when you properly do the evaluation, we talk about evaluation in text retrieval. People ask, how can we turn a parameter? Right? You did ask in assignment about some of the questions in assignment 1. So here we have the same situation that you might want to train your model. So when I say train your model, is in fact to calculate the similarity. So you need to have a split data into training that is used to calculate similarity. And you have the test data. You want to make a prediction and to see whether the prediction is correct based on the test data set. So what you can do is that you can split the data into training and test and repeat this t times. So this is called cross-validation, which allow you to have more data to train and more data to test. So evaluation is that you would, based on the training data, for a given user, you generate this top-end recommendation. And look at the test set. Because the test set, you basically hold out the highest sum of the ratings the user give, right? So you can look at whether the top end is indeed pick up the top end items in the test set, and to see whether how accurate that it is. So there's a measure called hit set. It's basically a measure whether how many of these hidden code out items are already in fact predicted and put in the recommendation list. So roughly speaking, there's two ways of doing the evaluation. One is called decision accuracy. So it's basically we want to predict whether that's given a recommendation, whether the recommended one is accurate or not. Another called prediction accuracy is that I'm not really care about how you can actually use it in the system. I got this metric, and therefore I want to make a prediction. I predict 5, and indeed, if the rating indeed is 5, and the error is 0. If the rating is indeed 4, then I have the error of 1. So you can actually look at this accuracy as well. So here, summarize some of these measures. It's quite similar to in what we talk about in text retrieval. We have recall position measure, and there is some balance between these two. And sometimes increase the n, which is top n document items you retrieve. You recommend it that you increase recall but decrease position.
Can I ask one question? Just to list the accuracy measures. With implicit data, how do you evaluate success when you're not just predicting things people are already going to watch? How do you infer from your prediction onto preferences?
Sorry, can you?
Just that step of inference where you go from predicting like what they're most likely to watch to predicting what they're most likely to like. There's in basket analysis, there's a clear kind of difference between the two, the notion of lift and things like that. I was just wondering, do you have anything to say about methods of going from what they're most likely to watch to what they're most likely to like / should be?
This is very specific about the particular way to use it. Sorry.
So I might not be clear.
No, I think you're clear, just like yeah, so it's really depends on what you actually based on. So in the training, if you're based on like, obviously,
it's easy to make like.
but in the training, it's actually the watch, then probably you're gonna predict the watch. But there's a link between these two. perhaps you might have some observation about that. You get an observation about 50% people liked, you can watch. And you can build a link between these two, right? So it really depends on
So
whether you would get that.
Kind of have to have some
Yeah.
knowledge of what people like.
Yeah.
Also, it's kind of the other way around. With Netflix data, they always predicted what people liked. But if someone rates like some sort of classical composer really negatively, some really obscure classical composer really negatively, that doesn't mean they have no opinions on classical music. I mean, it doesn't mean they hate classical music, it just means they have strong opinions on it. Does that make sense? Is there any, again, there's not really any particular formal way of dealing with these things, is there? From what my impression is.
Yeah, I think that what you actually mentioned is beyond what we're talking about.
Okay.
We can obviously talk
Yeah,
about
yeah.
offline, about what the specific problem you are dealing with. And certainly there's a possibility to deal with that.
Oh, right, okay.
Yeah. So the measure, we have the measure similar to what we talk about in text retrieval, right? So we can have the F1 measure, as balance position recall. So, but this is two slightly different measure where we're looking at the prediction accuracy. It's very easy, in fact. What you can do is that you would calculate error. You have a prediction, let's say a little head on top of the R is your prediction. And then you have your ground truth, which is say 5, you predict 4, then the error you get error 1. And you're averaging all the errors that you got. This is called mean absolute error. And then using this as a metric, see the lower the better. To see the prediction you get is how low that will be. You can compare with different algorithms. Another one which is talking about is quite similar, called root square error. It's that squared errors, which is sometimes quite good because when you square it, it's easy to directly optimize it. When we talk about SVD approach later, we will show that how can we directly minimize the square error. So here are some experiment result. If you look at mean absolute error, and this is the similarity we talk about. We talk about cosine similarity, which is here. We talk about Pearson correlation. We talk about adjusted cosine similarity. So this is basically for the item-based. You find in fact adjusted one is better because they have a low error. So it's again, this is my only host for. This is my only might be true for these movie lens data, but not necessarily be true for other data. But in general speaking, the adjusted cosine has much better performance. If you have different data set, you can obviously try. Another is to look at sensitivity of parameters. You look at the training test. So when we talk about training and test, we talk about the split training and the test into different sets. And you can see that if you have the x-axis here is how many of these users you put in the training. If you said put more training into the put more user into the training data, you can find that you can improve in general. You can improve this performance. That means obviously you have more data, therefore you might have more robust prediction. So equally for the number of neighbors, basically number of users, number of similar users you're going to choose. You can choose all the users, right? Weighted by their similarity measure, or you can choose top 10 or top 5 or just one similar user. And the performance is in fact different. If you look at these two graphs, it shows that there's certainly some optimal number of levels given the setup you have. So if again this is something that you might want to, you might be looking at, you might need to definitely take into consideration. This becomes one of parameters in your method. You might want to ask, okay, the item-based, the user-based, which one is better? And so this graph basically shows that, in general, item-based perform quite well. It's a little better than user-based. And again, this is really dependent on the data set. But in general, user-based, using user to calculate similarity is better than, using item to calculate similarity is better than calculate similarity between users. So, and the reason why, when you come in with a similarity measure, it's better to calculate similarity between users, between items.
More likely to find items that match closely than users that match closely.
Sorry?
It's more likely to find sets of items that match well, but users might not. They might diverge at various places, and therefore become less accurate predictors.
So that might be one reason. Any other opinions on this?
Content doesn't have temporal changes.
Yeah. So that might, another reason might be temporal. Temporal changes. Items might be more stable. User might be. So not all this suggests that the similarity between users may not necessarily be stable, whereas item-based similarity might be relatively stable. Therefore, when you calculate that, it might, when you calculate similarity, indeed they are similar. So,
sorry, what do you mean by stable?
Well, when I say stable, is that when you say these two users similar for the past, for the rating that we reached in the past, that means they're also similar in the future. So therefore, when you have that, you might have, if that is the case, then the prediction obviously would be good. But it seems that the user-based would be better from that perspective. So that's why it's quite important to have statistical or probabilistic justification about user-based and other item-based. Because if you do this proper mathematical modeling, then you would be able to understand what is underlying assumptions between what is underlying assumption in user-based model and what is underlying assumptions in item-based model. And then you look at these assumptions to see whether this assumption is valid in practice. And that might be a very thorough or very sound, a reasonable way to explain why the performance is good, why performance is better or worse. So that's why I think I'm going to spend a few slides talking about probabilistic justification. Therefore, you would be able to get an idea, okay, maybe because the user-based assumption, I make this prediction, is in fact, I have this underlying assumption. Therefore, this assumption perhaps compared to the item-based is not really true, in practice. So that sort of things. So a little bit math. Let's say, I believe you're familiar with normal distribution, Gaussian distribution. Here is very simple. It's a very simple math. Here, let's say you have two random variables, x and y, and they follow normal or Gaussian distribution. So they are independent. So it means that they are, in other words, they are correlated, let's say. Because they are correlated, therefore you can calculate conditional probability. Given that I know y, I want to predict what is expected value of x. So if you write these expected conditional expectation of x given y, you can actually write in the form like this. So if I know y, I would want to calculate the expected value of x. You can consider expected value as average. If I want to know the averaging value of x given I know y, and it will equal to, say, the averaging value of x, expected value of x without know anything, and add the bit that is related to y. And so the variance here is that you have variance of x divided by variance of y, and then there's a Pearson correlation. So here is the Pearson correlation. So if you have assumption about these, say, the variance of x and variance of y are the same, and then look at that, you actually can get rid of variance and only using the Pearson correlation to build a link between the y and x. If you do that, then think about what we actually calculate in user-based collaborative filtering. This is the formula we have, right? And we can in fact build a correspondence. So what we have is we can consider x is a user's age rating we want to predict, and y is another user case rating that we know already. And based on this, say, if this user's rating follow normal Gaussian distribution, and therefore we would able to come in with the prediction exactly follow the Gaussian distribution. Therefore, that is it. And look at the formula we're gonna have in the user-based collaborative filtering. In fact, you can build a correspondence. So this is basically a mean of this user without know anything. Without know anything, the best guess about this user's rating is obviously the average of this guy's rating in the past. So this is basically your average rating. And then if they think this variance of these two random variables are the same, then here you only calculate Pearson correlation, where again we're using Pearson correlation, but we also say, okay, in the standard, common collaborative filtering user-based approach, we are not only using Pearson correlation, but also using cosine similarity. But that means the similarity stuff is sensible here. And then this is the no rating subtract is the average rating. That's it. So this is basically saying, okay, it seems that user-based makes sense, but it does have some assumption underlying. So this is one thing. This is what look like if you want. We have no one rating. We want to predict another user's rating. But if you have top n most similar users, what's gonna happen? So this is the formula that I quickly come up with. For, let's say you have two ratings, if you know two similar users, if you know two ratings for similar users, and then you could come up with this prediction. It's a little complicated, but if you have a certain assumption, then you will actually reach to this quite similar formula as we formulated in the standard user-based collaborative filtering. So if you consider that these two neighborhood users are so it's independent. So these two neighborhood users are independent. Then we can get rid of correlation between these two neighborhood users. Therefore, you would get the averaging value, and then this is the rating prediction from user rating y, y1, and this is a prediction for y2, and you put it together to get a result. So this is rating by other similar users, and this is similarity score, and you put it together to get a prediction. So what I try to say here is that from this probabilistic formulation, you could actually see, okay, we do have a user-based computing, we do have some assumption underlying, and whether it works or not, it's really depends on whether this assumption is sensible or not. So this will help you to do a proper analysis. So we would talk about recommendation. We basically say that in fact it's a prediction problem that you have a big user item matrix and you want to make a prediction for the missing data you got. And one way you can look at is obviously looking at users and try to similarity users and make inference from these similar users rating. But you can also look at it from similar item ratings. And so some of the study basically show that in fact can combine these two together, and therefore you will have a much better result. And in the end, if you look at what happens in the Netflix competition, is the best ones is always combine all the approach together. So it's not just single approach. It's some people using hundreds of methods combined together.
How do they blend? Sorry.
Blended together.
Any techniques that they use?
Well, there are tons of techniques combined.
Logistically.
In the next session, I'm going to talk about
Okay.
SVD, and they're in fact called the boosting approach, which is a way to combine a different approach.
So,
It turned out to be in fact quite effective in those competitions. So I think we can take a break, 15 minutes break, and then we will come back later talk about this SVD approach.